wait, we're allowed to do that. Okay, yeah.
Okay, I'm definitely doing that then.
Like I missed 4 points. I did my 2 corrections, and then she bumped me up to like a 99 instead of 92.
Did she? Yeah, I did horrible, but I had like horrible test anxiety. So, like I can do everything else perfect, but we can just do a test like right now.
I know people who will literally have a conversation about it, but then you like say you take the test after what you just talked about.
Yeah. Exactly.
It's like just Men in Black memory lesson.
The first Men in Black is like one of my favorite movies ever. Like I don't like rewatching movies except for Men in Black for some reason, and like a few other really good movies.
Well, they did a really good job on that series up until the last one, in my opinion.
Yeah, I didn't mind Men in Black 2, yeah, but
Yeah,
yeah, Men in
the
Black
first one
3.
was kinda like, what, dude? They were reaching on that.
I love the cartoon series though.
Yes. That's what I'm saying. The whole Men in Black series, besides the third one, is actually pretty good. Like they even did the, what are they called? The shorts of the little alien guys.
Yeah.
Yeah, they did like a little short series on them, and that was funny.
Oh.
It was pretty like comedic. I liked that, but so basically it's just a short series following those little alien guys doing like dispatch at the
Man.
office.
Like who doesn't love coffee addicted aliens?
I know, right?
So we can do test corrections on our exam?
Yeah.
Okay, I did not hear that.
Oh. So yeah, we can do test corrections. I think I'm offering 75% back.
Perfect. Can I turn in Monday?
Yeah.
Okay.
And everyone's here early.
I thought I was gonna be late today.
Yeah. Oh, I actually brought s'mores.
Oh, nice.
So I'm going to save them for lab time. Since we'll have
Hopefully he remembered the sticks.
Yeah, otherwise, I don't know what we'll do, but we'll just eat them without burning them. Yeah. Did you get 2 bangs today?
No, this is the other one from Monday.
Oh, nice. Conservation.
Well, if I drink 2 bangs in a single day, oh my god, I'm pretty sure I'd have a heart attack. As is through the whole test, I had like the jitters. I was like sitting there like this. Let's do this, come on.
Yeah, caffeine is like dangerous.
Well, it's not just the caffeine in here that gets you. They put so much in here. They used to put creatine, but now they don't.
Oh, dang.
That made it even worse. Made you feel like your skin was on fire. There's what's the one? There's a new energy drink line that has so much caffeine and creatine and like a bunch of like basically pre-workout in it.
Oh my gosh.
To the point where they're like kids under the age of 18 are having heart attacks and stuff like that. So now they put a label on it like under the age of 18, please do not drink.
Whoa.
Yeah. I think it was like Logan Paul really doing one or something. It's one of the Paul brothers. I don't remember which one.
one of them. I'm pretty sure it's Jake.
Yeah, Jake, there you go. The one who does the boxing. Yeah, yeah. Yeah, because he has 2. He has one that's like just a regular energy drink. It's like 100 or like 200 milligrams caffeine just for everything, and then the other one's like an amped up or whatever.
Now I'm looking at this.
Yeah, there you go. Yeah, those things. They were having like straight up heart attacks and stuff like that.
It contains almost 6 times more caffeine than a standard 12 ounce.
Yeah, those things are like literally liquid cocaine in a can.
still funny to me, like, what substances are legal, illegal. It's like, you can have all the caffeine you want, but it may kill you. Or like, remember when they were selling powders of caffeine or something that you were supposed to mix? And then people were like, yeah, well, that's crazy, because people will like crazy OD on that and die.
So there's one that you can get, they're not super strong. Pop Fizz, that's what it's called. Pop Fizz out of Costco. You can get these little packets, they're like flavored like Neo flavor, but they hold like 125 milligrams of caffeine.
Wait, where are these?
Pop Fizz. But people were using them to do flavored energy drinks because they just thought they were made for like flavoring energy.
Oh,
drinks.
no.
So people were taking like Bangs and stuff, and Monsters and stuff, and adding 125 milligrams of caffeine. Yes.
Oh my gosh. Did they
So
die?
They were getting things that were like over 300 to 400 milligrams of caffeine in a single can.
Yes, and then what, do they have heart attacks or?
I don't know, for a lot of people have. Like,
That's
like,
crazy.
that's why Redline stopped making energy drinks a long time ago.
Mm.
So, Redline was like the original one that kids were having heart attacks on because they had a challenge. They had they called it the Redline Prime, or Redline Supreme or something like that. This was back in like 2011, and high school kids were taking it. They were 24 ounces, 450 milligrams. They told you it was 3 servings. The kids were trying to pound it and like chug
Oh
those
my
as quickly as they
gosh.
could. And they were like we had a kid who actually had to get taken to the hospital from North because he ended up like just straight up like seizing up in class, and they had to take him to like to cardiac arrest. Yeah, that drink only lasted about a year, but Redlines were out for a while. They came out with that to combat the Monster imports and the Monster BFCs.
Yeah.
And then that was pretty much it for them. Now you can find Redlines every once in a while, or like a few stores, but they only sell the small ones.
Crazy stuff. All right, that was a good warm up. Chemicals.
How does it work? Your synapses in your brain.
But caffeine is legal, perfectly legal. Anyways, other topics for another time of legalities of chemicals. So we were in the middle of Le Chatelier's principle. So let's kind of orient ourselves again. And so let's look at this first scenario then, this other chart that we hadn't looked at. And so orienting ourselves with Le Chatelier's principle. So reminding ourselves of the reaction we were looking at. So we were looking at, right, this dimerization reaction. And so now let's look at what's happening. So again, we were at equilibrium. And so now we add, in this case, it's going to be product formally. So we're adding more product. So we artificially spike it, open our system. We can zoom in a little bit too, hard to see. And so of course, after we spike it with our product, so now this forces it to go the other way. So now back in reverse, favoring our reactant formation, so favoring the dimer. And so we see that, right? So now more dimers being created until your new equilibrium is reestablished. And again, your K does not change through this. Let's go, oops. And so let's kind of go through some of the text. And again, we can see how it just shifts. So if we remove a reactant, and again, we mentioned that it has to be not a solid or a liquid. So solids, adding them doesn't change the reaction rate or affect equilibrium. Adding like a pure liquid reagent doesn't change the equilibrium because it's just neat concentration at that point. And so of course, if we remove reactants, so removing a reactant initially decreases the rate of the forward reaction. So that makes sense, right? There's less of it, so then it decreases. No initial effect of the rate of the reverse reaction, but now it's going faster in reverse, since it, again, comparatively speaking, decreased the rate of the forward reaction. And so now we have it favoring reverse. And then it creates more reactants, so again, trying to restore your reactants to equilibrium. And so we mentioned, so this is all right, a kind of confusing way of saying that, yes, we'll use up some of our, add back some of our removed reactants, so we'll make some more, but not as much as we had before, and it just finds its new equilibrium system. And again, K is always unchanged as long as we're at the same temperature. Let's see, so this is just adding a reactant then, pushes it forward to the products. So let's look at some, oops. Oh no, I thought I had practice problems.
Which K is just the ratio of product over reactant, right?
Right. Uh-oh. All right, let's look at our next section. So the next little bit is about catalysts. And so what's a catalyst? Or examples of catalysts. Yeah, so it speeds up a reaction. Ah.
We were just talking about it. I remember.
And we do have s'mores today, so looks like we'll have some fun in lab. Yeah, we'll be burning stuff and burning stuff, which is good. It's a good lab for it because there's a lot of downtime potentially with heating and waiting and heating. Excellent. So yeah, catalyst speeds up a reaction, but any examples of catalysts that we can think of? So yeah, lactase. So lactase, right, that breaks down the lactose sugar. Other examples?
Anything with ace. That's all I know, but I don't know of any.
The ace of spades.
It's funny, but I like it. Anything with ace.
But I don't know any more examples.
Okay, Sean Dark, is nitrates a thing?
Nitrogenase, yeah.
Close enough.
So yeah, there's a nitrogenase, which is a catalyst that speeds up the reaction, so that allows nitrogen fixation at room temperature.
Just add an ace.
It's not glucanase.
Could be.
Pretty sure it has a long name for that, doesn't it?
I don't, you know, honestly, as soon as you said ace, like all the enzymes I was thinking like vanished in my head for some reason.
Me too. No, I didn't know any beginning.
Like, what's the one in your saliva?
Oh, that's,
Saliva.
Amylase, that's what it is.
which helps break down carbohydrates.
Yeah.
You got that?
And then we could also add in there, right, our catalytic converter for our cars. Those are all good examples. Excellent. So catalysts are pretty fascinating. So they are substances, again, that affect the rate of a reaction without being consumed. And so they're always in smaller amounts, at least relatively speaking, to the reactants and products. And this is really cool because catalysts actually provide just a whole different mechanism. And if we were to look at like Grubbs catalysts, which are some chemical catalysts used in olefin metathesis, we would just see, right, how they make a whole new compound which provides a whole new pathway. So the same thing with any of our ACEs, right? And everyone always says that kind of lock and key. So the enzyme matches a substrate, holds it in place, allows your reaction. to take place. And so looking and just kind of comparing the mechanisms, so this is a slow reaction. So we have ozone plus this radical oxygen gives us 2 equivalents of O2. But then we can catalyze it. And so again, notice how you make this intermediate, which involves your catalyst. So it's involved somewhere, but then it's used up, and then you recover the catalyst. So that's always your key. At least ideally, you would like to recover the catalyst. So as a practicing chemist, so it depends on your catalyst and whether you can recover it or not. So sometimes people use like palladium, platinum as catalyst, but that could be harder to extract, so it's just kind of gone. If you were on an industrial scale, you'd probably really want to recover your catalyst or have like a solid state catalyst like your converter, but there's difficulty with reactions if you have different mediums, so like solid and air, that can be difficult. And so something that we want to take away from this is, again, how it creates a whole new pathway. So looking at our energy diagram, so we can still tell, so what type of reaction is this? Endothermic, exothermic?
Got 50-50 shot. Endothermic.
Wrong way.
Dang
No gambling for you. So yeah, it's exothermic. So remember, the products are lower. And then so that tells us that all this energy is going to be given off as heat. So exothermic.
So it's being released then, the energy's being released.
Yeah. So the
Okay.
products have less energy, so the other energy has to go somewhere. So it's heat. And so what we want to take away, so yeah, still same starting points and ending points thermodynamically, so that doesn't change. But what does change is this pathway. And so comparing, right, our uncatalyzed pathway, it's going to be higher in energy, so it's going to take more energy to make this happen. But now with our catalyzed pathway, so now it goes through 2 steps, and then those 2 steps are lower in energy, and so now it would have a lot lower activation energy. So this would be activation energy 1, activation energy 2, so it goes through 2 steps, but overall lower and more favorable than trying to achieve this 1. So it creates new pathway is what we want to take away. And so most catalysts are used to speed up a reaction, so they're called a positive catalyst, or usually you just say catalyst. And so you could have a negative catalyst, but what's another name for that usually people use instead of negative catalyst?
Anti-catalyst.
It's a good guess, but
Sounds cool at least.
other guesses?
So slow down a reaction?
Yeah.
I think it's in the book.
So it's called an inhibitor. I actually don't know if it's in the book.
Oh, then that's just.
I gotta tell you other terms, because no one goes around saying negative catalyst. They would say you want to use an inhibitor.
Oh, yeah.
So sometimes your book isn't the end all means all. And so this means if we have a homogeneous catalyst, all species would be present in the same phase. And so this is what I was saying, this might be harder to recover a catalyst from if you're using, think about you're throwing in a bunch of powder reagents to a mixture, and then you have to get it out. So that would be difficult to recover a catalyst from. Not saying it isn't possible, but for small scales, you usually don't recover the catalyst, unfortunately. But you have anywhere from like a 1% to 10% loading generally. So you try to keep it low, so it depends obviously on the efficiency. But then if you have a heterogeneous catalyst, so species are present in different phases, again, like your catalytic converter. And so sometimes this can be considered more ideal. Again, this is just in general. But in some sort of industrial setting, you probably want to have a heterogeneous catalyst, or even thinking about the scrubbers, right? So that's a physical material that the gas passes through, and so the sulfur reacts and binds. So again, different mediums so you can separate substances out or use your catalyst over and over again. So obviously in industry, even though it seems pretty small, right, 1 to 10% throwing away your catalyst, that would get pretty expensive over time. Again, not saying it doesn't happen, but that's where, you know, some of these designer drugs would get a pricier price tag, is because of the catalyst. That's all factors to consider. All right, I think that we finished the chapter, but I think we should do some practice on probably chapter 5 is giving people struggles, moles, reactions, all that, unless there's questions from chapter 6 that we want to hit up first. So I guess today will be a good review catch-up day. But I think the moles is what people probably have the most struggle. Other comments? All right, so let's start with our problem. And we're talking about nitrogenase. So let's just write the reaction for the Haber-Bosch process. So that's going to be the reaction of ammonia, of nitrogen and hydrogen to produce ammonia. All right, so start with this. And we'll probably put it, oh, that's what it is. So the Haber-Bosch process is a reaction of nitrogen and hydrogen to produce ammonia. So it's super famous. That's where a lot of energy consumption goes into, is producing ammonia. These reactions happen at extremely high temperatures and pressure, so it takes a lot of energy. That's why we just talked about nitrogenase. That would be wonderful to somehow make your own synthetic nitrogenase catalyst, or a biomimetic catalyst really is what it would be called, and do this not at these temperatures on the industrial scale.
So what all are we doing here? Are we just writing out the,
Yeah, just writing out the balanced equation.
okay, cool.
I'm just setting us up. We're going to do a series of problems, but I want to do it step by step with everybody.
Like moles and all? Like,
Yeah.
What are the sig figs, I guess? Or no, sorry, coefficients.
Yeah.
My terms mixed up here.
So do we have this equation so far? So nitrogen and hydrogen to produce ammonia.
And aren't they both diatomic?
Yeah, you want to put it on the board for us? Do it on the far board. Oh, Emma's going to do it.
Okay.
Sorry. But yeah, they are diatomic, so that was the trick, or the first trick. Yeah. Yeah, just so we can we'll put eventually the whole problem on there. nitrogen, I think you just wrote funny, because it should be N2. Yeah,
Because it's nitrogen and hydrogen combining together to create ammonia.
yeah, so that would be your product. So it's nitrogen and hydrogen to produce ammonia.
So it's like,
You want to try?
So it actually means like that, right?
Yeah, just one arrow, because we,
So would this be a back and forth, or would this be?
I would just put a single arrow.
That's the part that I was.
Yeah.
confused with.
Although actually it is an equilibrium, but not for our purposes.
Okay.
not yet.
Not till you take my other classes. So
I'm
we,
already lost. Like,
wait,
I don't-
what? How are we lost?
I know, because it's chemistry.
Because nitrogen and hydrogens are diatonics, you have NH3, you have to equal it out, so.
So they always have to have,
Well, yeah,
The
so,
natural state is gonna wanna be in twos.
right, so that's why they were highlighted on our periodic table.
so no matter, every time you put them in an equation, they're always H2 and N2.
Yeah. So anytime you,
And then you just have to, but it's N2 plus H2. And
Yeah.
you're saying it's making NH3.
yeah, so N2 plus H2 gives NH3. So this was kind of like step 0.5 or 1, however you want to break it down. Right, so once you get there, okay, I at least rewrote what this is saying. But then we have to balance it, because like you said, oh, it makes NH3, so now something's messed up. And the easiest way is to put a 2 here, so 2 times 3 is 6 hydrogen, so then 3, so now we have 6, and then our 2 nitrogen is balanced. So we okay with this part now? So it's just a lot of practice with chemistry, like I promise. Remember, I've done this like 5 million times. So now, let's try our problem. So if we have 20.00 grams of nitrogen and hydrogen, which is our limiting reagent?
Wait, is that, and, okay.
So I'll give people some time to start that. What do you have to do? What do you have to solve? We could even put what basics we might need to start off with on the board to help remind everybody. All right, always start with all your knowns.
So is that N2 and H2? Sorry, I can't see the symbol in the middle.
Yeah, and.
Okay.
if, this is one of those problems where we're going to convert a bunch, like to moles to,
Yeah, so we might have to do a lot of converting.
what are we converting to though? I'm not entirely sure I know what limiting reagent means.
So if it's our limiting reagent, the easiest way to set this up is kind of find who produces the least amount of product. And so I left it kind of ambiguous on purpose, because I didn't tell you to put it in moles or grams, so you could do whatever you choose. So you could stop it at the moles. And so then what we need to do is convert, right? So if we have 20 grams of nitrogen, we need to convert that to moles of nitrogen, then use our conversion factor, right, to get moles.
Oh, okay.
Yeah, of ammonia, and then, like I said, we could stop there. I'll probably ask us in the next question how much, product that is, but we'll get there. And if, yeah.
Did you ever hand out that sheet, the mole, cheat sheet?
Oh, the highway, I did.
I don't.
Let's see. See if I have a copy on me. I'll have to give it to you in the lab, I think. I don't know. Yeah, they're not on me at the moment. They might be in my office. So.
And would you time to weight twice because it's a diatomic?
Yeah, and so maybe we could start with that by putting just a massive N2 and H2 on the board. I don't know if.
I got the wood, okay.
Let's see. Does anybody want to do it other than Josh?
How many sig figs do we?
Yeah, go for it. Go for it.
Sig figs?
I've only got the first half done so far.
Yeah, at least what you have. So all I want is the molecular weights of N2 and H2 to start with.
Oh, just a moment, okay.
Yeah, just get people going. Yeah, probably on that board.
Are these for excellence?
Oh, yeah, those are for racing. Oh, probably want to keep the equation on there, so you can just.
Alright, so that's that one.
But if you did want to start writing the next half, you can, but I was just looking for molecular weights.
Okay,
Get
I'll just
people.
give the weights then.
Cool. Excellent. All right, so good. So don't fall into any traps initially with these diatomics again. So rate double the weight. Does anyone want to start setting up this next part for us on the board? Okay, go for it.
So using no numbers, or do we set up with numbers and all?
Yeah, I would set up with numbers now.
Okay, so 20
You can move like all the way far left and start
Yeah,
there.
I guess I think I can do it. I'm just doing this right here. Yes, okay. Times N2, then that's times 1 mole of N2 with an S, which is 28. So what sig figs do we go to? Do we go to like the 28.014?
So that's kind of up to you. So, right, notice how Emma put 5 sig figs there. So that means you can at least take it out to the 4. So I would try to at least conserve what you're given.
Oh, yeah, because I did it
Because
to
you
the
can
4
use
sig figs.
extras, right, and that's fine.
Yeah, because I did it to the 4 sig figs. Cause
Yeah, and
yeah,
that's,
the 20 was okay.
so that's fine. So yeah, there could be differences with rounding. You know, you could have just rounded to 28 and 2. But yeah, I would usually just refer to what you're given for your sig figs.
What about my answer, or?
Yeah.
Yeah, I got it. Is it moles or grams per mole?
Yeah, so right now it's moles. So you did all your units correct. So this leaves us with moles of ammonia.
Yeah, so is that good, or did I need to change it to something else?
No, we can stop here at moles of ammonia.
I'm not sure how I need to convert.
Well, that's also what I'm trying to show you here. Because, right, you could take it to moles, but you could have taken it to grams too. And that would be, it's still going to give you the same answer. It's just where we're at. So is everyone okay with that? So that looks good. And so note, right, the unit cancellation on this, so this looks good, right? So you can follow grams cancels, moles of N2 cancels, moles of N2 cancels.
I get stuck on that one right there.
On
When you
which
go
one?
back to the equation and you pull it out of the equation, and he tried to explain to me like twice, and
This one?
yeah, I get stuck right there.
All right, so this is, where's another marker? There's a red one somewhere in this room, I thought.
And I did in the homework too, that's why I would get, that's what you were asking about too.
Here's the red marker. So all this is pulling out is essentially just a conversion factor, right? Like it's just a ratio.
So if we're looking for, okay.
So it's just a conversion factor, so it's a ratio, I'm sorry, this one sucks, from our balanced equation, right? And so it doesn't matter what this ratio is, you just always refer to this one, your equation, and then look at what you're talking about, right? We're looking at nitrogen, we're trying to go to ammonia, so you're thinking, you can even put over here what units you want. Well, I want my answer to give me moles of ammonia, so that means I need moles of ammonia on top. So then I'm going to compare, right, my N2 and my ammonia ratio. So that's where that goes into play. So does that kind of make sense? And like, think back to the graham crackers, right? So we'll play with graham crackers in class again, but like, think of it, right? So we have like 1 graham cracker and 3 chocolates or whatever. You can think of that, you know, the same thing. Like, gives us, obviously it doesn't work that well with a graham cracker, but makes 2 Frankenstein s'mores, whatever. Right? So just kind of refocus it in your brain, or, you know, baking. 1 ratio of cups of sugar to 3 eggs gives us a sugary mess, right? 2 cups of sugar mess. But you get the point. It's just a ratio. All right, so this looks good. So we'll stop here for moles for a second. So who wants to do the hydrogen now? Do the same setup, except just with hydrogen. Let's see. Let's give someone else
I don't know if this will help anybody else, but when we used to do long conversions, a trick that helps me is sometimes I'll give myself a lot of space. I'll start with what I have, and I'll write way down the line what I need, so that way you have your 2 top lines, so that way you always put what you want to cancel on bottom, and then you try to use that to get to where you want. It's almost like
Yeah.
you're doing a maze of a puzzle at that point. And sometimes visually doing that helps.
Yeah. And that unit canceling, I speak from experience, will get you through physics, because I didn't quite understand physics, but I can cancel units. So who wants to do hydrogen? All right.
Oh, yeah. Well, now that I have a small little copy.
Yeah, and try to
Oh,
squeeze
wait, I
it in.
didn't do the math yet. Oh, no. Did I set it up right? Hold on.
Yes.
Okay.
Okay.
I didn't.
6.6. 6.4.
What is it?
6.614.
What did I miss?
Oh, you did it. So no, it's NH3, not H2. That's your problem. No, no, you're good. So it's moved to
Oh,
NH3.
this.
Yep.
Yeah, and you could cancel your units, right, and to see that, so cancel, yeah, that cancels, H2 cancels. Yeah. So yeah, you're left with moles of ammonia for your units. And so now we can tell, so which one's our limiting reagent?
Wait.
Oh, yeah.
Oops, and I forgot to copy.
Now is this where you do like this over that or something?
No, so right now we're just looking at them, so we just compare. And now I'm behind on my notes.
So nitrogen is only 1.428 moles of ammonia per 20 grams of hydrogen. Means 6.614 moles. So nitrogen will limit how much ammonia you can actually, you'll have an excess amount of heat. I keep wanting to call it helium for some reason.
Yeah.
I feel a little bit different.
Yeah. So let's see.
Saying that, wait, hold on. So does this say nitrogen? Say that again.
So with 20 grams of nitrogen and hydrogen,
Yeah.
you can make 1.428 moles of ammonia from the 20 grams of nitrogen, but you can make 6.614 moles of ammonia with the 20 grams of hydrogen. So that means that you'll have excess hydrogen, and the nitrogen will be your limiting reagent. I'm struggling to speak today. Not much, right?
All right, so the last question, while I copy all the beautiful work on the board, is so now we can determine the theoretical yield of the reaction, right? So basically, using whatever limiting reagent we found, which we all agreed, nitrogen. So now using that amount, and you can start with the moles for this problem, so you don't have to rework everything. But now determine the theoretical yield, so make sure you're familiar with that terminology so it doesn't scare you later. And then if we recovered 14.67 grams of ammonia, what was our theoretical, or our percent yield?
What's the one word after the, of the?
Theoretical?
Those RXN?
Reaction?
Oh, reaction, okay. So we need to transfer our answer as moles, transfer it to grams?
Yeah, so that's what I'm asking here now. So we can start, right, so we left ourselves in a good position, so we know how much product we're gonna get, right? So we can go back to this answer. Well, this was my limiting reagent, so this means, right, we're gonna make this much product. We're gonna have 1.428 moles of ammonia. So yeah, all we have to do is convert it to grams from there.
And so it basically just, okay.
What? I can't read lips. You wanna put it on the board? You gonna finish it? Oh, is what a 4 or 9, sorry.
The moles of ammonia.
I think it's supposed to be 1.428, but I didn't plug it in.
Yeah, that's 1.4, my bad.
What, we're lost? You can't be lost. You were found, I thought. You put up H2 for us. You gave us the answer. You're right there. See, I don't know if we're lost. We just got to write down. It's all about reorienting yourself and like, all right, what do I know? Where are we at, right? There's a lot of labels on things. That's why you got to label everything.
Do you want me to do the other part too, or wait?
Yeah, might as well put it on there since it's not. So this looks good. So did people get that for the final amount? We just take our moles of ammonia, and the molecular weight looks nice, 17.
Where did you get the 14 from?
Oh, just my head.
Oh, that's where it came, wait.
Yeah, just from the problem. So it's just.
Yeah, I grabbed that. So that's creating the percentage based off of what you actually got with theoretical.
Yeah, because that could be just a random amount, right? So all it is what you actually weighed in lab.
Oh, it's what we covered, my bad.
Yeah.
Okay. Now I see it.
And yeah, so then that last step is just dividing what we actually got in our hands after dropping half of it on the floor, whatever happened.
Forgot to put the cap on, the gas got.
Yeah, exactly. I've seen all sorts of stuff.
So we take the lesser mass and use it?
Well, it should be a lesser mass, but it's whatever's given to you. So you could actually have over 100% yield, but then you'd say, oh, your reaction is probably impure.
So you take actual over theoretical.
Yeah, so let's write that. So actual over your theoretical, and then of course times 100.
So you're saying the 14.67 that you gave us is the actual?
Yeah, so like once you're done at the end of the day, this is what you actually had, And if I'd have given you, oh, we got 25 grams, then you would say, uh-oh, you know, you over 100% yield, probably impure, maybe you still got hydrogen or nitrogen floating in there, something's wrong.
So that 17.04 is the molecular weight of NH3?
Yep.
Okay, good.
Wait, why did you decide to use the,
Which one?
What question?
why did we use the 1.428?
Because it's the smaller.
Oh, it's the limiting?
Yeah, so whatever one's the smaller amount, right, that's the limiting one, that's the one that runs out first.
So we want to say, so why do we want to use that one?
Because it's the smallest amount.
So you just always use the limiting one?
Right, because it's
Rather
gonna
than
run out
yield, rather
first.
than yield.
Yeah. Yeah, because it doesn't matter, right,
Okay.
how much hydrogen we have, we can keep going with the hydrogen, but the nitrogen already ran out, so.
So, got it.
Right, because this is, again, what you're doing in the lab on an everyday basis. You look at your reagents maybe, probably look at the most expensive one first and say, how much am I gonna blow? And then you go from there. All right, are we ready to try this again? Yeah, I see.
So I could definitely see a practical use of like figuring out how much of each you had if we had like a budget. So that way.
Well, you're always on a budget.
That's what I'm saying, but like ultimately utilize as much of each as possible.
Yeah, but yeah, it's either you're on a budget or safety concerns is where you're trying to limit to.
Well, they have blast doors.
You know, it's all fun until your reaction ends up on you and all your fume hood because you scaled up too big, speaking from experience. And it wasn't even that big. It's only trying to get 20 grams of product. Anyways, let's try another one. Let's see. Right? Oh, I don't know why I put an E on the end of combustion. Yeah. Oh, and I didn't even erase it. Oh my gosh. Did you know we're hiring a bilingual biology instructor, by the way? Required. Is it? They're going to teach classes in Spanish, allegedly, in biology. Who's ever done that at any college?
We have a very large Hispanic population.
Oregon's like the top 10 whitest states, man.
No, that's like northern Oregon, though. Anything from, what's it called, Bend up. Like, go to Bend, yeah, you're right. If you see somebody who's not white, you're concerned about them. They are not there by choice. But, like, southern Oregon, come to my church. I'll show you.
Okay, what church?
Shepherd of the Valley. We have 3 Spanish masses for 1 regular mass.
Okay, I'm gonna look
I
into
will
this
tell
now.
you, we have some straight up awesome festivals and stuff like that. Like our last one had homemade carne asada and like the corn with the mayonnaise and
Yeah. Clearly I've been church shopping in all the wrong churches.
when we do our fall festival, they do, they actually do like the dances and stuff with the swords and the dresses. I don't know what it's called.
The Florico thing? Yeah.
They do homemade, chorizo, like the breakfast burritos and like the
All right, well, we're all gonna go to your church now, 'cause
I will tell you, it is the most bonkers whenever we do our
Yeah, you got me with like chorizo burritos, so. Yeah, this one's a tricky one. Write the equation for the combustion of ethane, and I gave you the formula for ethane.
So for combustion, I might be giving too much away here, but for combustion, you have to force oxygen in, and it gives you H2O and CO2, right?
Yeah. So we'll start,
Because the part that always gets me is because it can be either CO2 or CO, right?
well, we usually assume a complete combustion, so just CO.
Always assume CO2 unless stated otherwise.
Yeah,
Okay.
and I probably wouldn't ever make you do an incomplete combustion, that'd be difficult.
Okay.
But yeah, so this was kind of, again, step one or, yeah, 0.5.
Right. I need step 1, 2.
So we had to recognize what the term combustion meant. And so, like Josh said, that's adding oxygen to whatever our organic was, so in this case ethane. And then we always produce CO2 and water in any combustion.
So will those three variables essentially always stay the same? The only thing that really changes is the first element?
Pretty much, yeah. And then this has to be a carbon, hydrogen, and maybe an oxygen, so it won't be that crazy either.
So combustion, it's when it adds oxygen and then CO2.
Oh, and then it makes CO2.
Oh, okay.
So then it always makes CO2 and water. And so now you'll have to balance that.
Combustion adds O2 and then produces CO2 H2O.
Yeah.
Like no matter what. Or
Yeah, so it always produces that. It's just now the trick is the ratios, right? So we know it always produces these things. We just don't know the ratio.
So I just want to double check. So no matter what.
You already
it
ready to
produces-
write it? Give everyone a second.
Okay.
So just like no matter what though, it produces CO2 and H2O.
Yeah,
Like no matter what's in front of the O2.
exactly.
Okay, I just want to double check.
Yeah, and this could also have an oxygen, right? And it would still produce CO2 and H2O.
Good, I'm just right. Okay.
So what's the term for combustion, at least what it was saying in the book, it says as long as you have oxygen on the reactant side with CO2 emitters, some kind of carbon monoxide and H2O on the other.
Yeah.
So technically, is it always gonna be a carbon, hydrogen kind of compound on the reactant side?
Yeah, for our case, for combustions, but of course we've seen like magnesium can combust, right?
Yeah. So
And-
like you could basically have anything, but for the most popular is gonna be
Yeah.
carbon, hydrogen.
Yeah, because usually the problem wants you to figure out the CO2 and water bit.
Okay.
And usually when we're doing these combustions, so if you were to take my 200 level, you like backtrack the formulas from the combustion, which gets so much more fun. So instead of doing what we're doing, or like in addition to, so you say like, you have so many grams of ethane, that makes so many grams of CO2 or water or whatever. And then from there, you have to backtrack the formula. Or no, you would say you have an unknown hydrocarbon
Okay.
of a mass, it makes this much CO2, and then you backtrack,
Okay, that's cool.
which
I have a
is fun.
question. Could you force enough CO2 and H2O together to like inverse a combustion reaction?
I would assume not. I think combustion's only go in one direction.
I'm trying to balance this equation.
Even,
What's up? Okay.
Yeah. So just cleared it. The markers.
So I was just gonna walk through the process I kind of went through. I had my biggest variable right here. Uh, So I tried to balance that out on this side first, so I went for 2 here. Just put it up here. Went for 2 here because I needed 2 CO2 or 2 carbons. And then I went to the H's, and this is where I ran into my problem because I needed 6. So if I were to do 3, that would give me an odd number for my oxygen, so that wouldn't work. So then we gotta go a step higher. So we put this one to 2. That gives us 12 carbons, or sorry, 4 carbons. And 12 hydrogens. Now I do the same exact steps. I'll need 4 carbons for this one, so I already know I need 4. This will give us 4 and 8. And for hydrogens, I need 12, so this one would be 6. So that would give me 12 and 6. And so now for the O2s, I just got to combine 8 and 6, which is 14. 14 divided by 2.
That looks good to me. Everybody get that? So these are always tricky to balance, but that was a good method, trying to balance out the carbons and oxygens first and noticing that they were odd or even. And you could formally balance with half coefficients, so sometimes you see that in like other textbooks. So if you had gotten, so that would give you like 1 to, yeah, so 7/2. So I would put, right, this is okay, then you have to deal with this half coefficient. But this is better, so it's better to balance with whole numbers, but just saying for your reference, you'll probably see half coefficients, especially with combustion reactions in textbooks or whatever you're looking at, so that's where it comes from. So it's still appropriate, but then you have to deal with fractions and your conversion factors anyways, so I encourage whole numbers, but not wrong. All right, so now let's do the next step. So if we have 10.71 times, was there just a car accident?
Yeah, they literally just a car accident right here. Oh, got him good.
Oh man, he ran into the taco place almost. What, how does that happen?
He hit him from the side, they both collided. It looks like it might have been the...
Oh, the police is already right there.
Oh my god.
Dummy.
ADHD class,
I
let's do
know.
this, guys.
The cop just like, what the?
Yeah, I'm not sure whose fault it was exactly.
Did he actually hit the truck?
Yeah, no, just
The taco truck.
Oh, not the truck.
So he missed it barely.
He barely missed it.
Oh yeah, they got him good. He blew out his tire and everything.
Yeah, front.
Dang.
Yeah, they did the whole quarter.
Imagine this was a
Anyways.
class and you turned it into an
That's a
equation.
good one.
Yeah.
No.
All right, guys, let's calculate the vector diagrams of the accident.
Oh my god. Real life experience.
You laugh, but that's how they figure out who's at fault in some accident.
Oh, yeah, I know.
They'll actually take like tire holes and all that stuff.
All right, so if we have 10.71, and I probably should have written that in proper sig figs, but, so 10.71 times 10 to the 26 molecules of ethane, and 2.88 times 10 to the 28 molecules of O2, which one is my limiting reagent?
I'm sorry, where did you get that number?
Which number?
Both of them, or both equations?
It's just a molecular.
What is my what?
Limiting reagent, sorry.
Oh, wait, you just gave us those?
Yeah, I just gave them to you
Okay.
right now, sorry.
Oh, thank you, Richard lost me.
You're like, let's do this. You did this a lot more further than I thought it was gonna have to be.
Okey-dokey, let's do this. I'm sorry, what was that word after my?
Limiting reagent. I gotta get with the lingo.
I'm not good at
She's
radiation.
like, they asked me every little detail.
Okay, you guys are troopers. Eight weeks for chemistry is no joke.
Oh, wait a second, wouldn't you convert this to moles and then convert it to, no, wait, wouldn't you just need to convert it to moles and then compare the two?
Well, you have to compare something. But, yeah, I think, oh, Richard's on the scene. Yeah, he's our maintenance guy. He's getting tacos, but he's really checking out the act.
Get tacos.
Yeah, it's too early for tacos now. It's 10 a.m. Taco time. As long as there's a car accident to look at.
I keep on calling them avocado, but I don't.
Oh, avocado's number?
Avocado's number. I mean, not even number, that's a formula, that's not even a number.
Actually,
Would we need to convert this to CO2 or H2O?
So I didn't say, so you could pick either one to compare. You could also try to compare it to each other, but some people get confused doing that, so
So just choose one.
that would be my advice, yeah.
And would you choose the same one for the next equation too as well?
Yeah, so if you pick CO2 for the ethane, right, pick CO2 for O2, so you're comparing the same amount of product. There are other ways to do it, because you could figure out, like, based upon this, how many moles of O2 do I have, and is it enough? But
Yeah. And when you put this in the calculator, you don't put times E, you just put E, right?
yeah,
Okay.
do you want to put at least the first portion?
Did you want me to do both of the C2H sentence for CO2 and H2O? I'll leave the other one for something else.
Do what? Sorry.
So I have both the amount of moles of CO2 and H2O.
Oh, you're fancy.
Do you want me to do both for C2H6?
Yeah, you can.
Okay, and then I'll leave the other ones for C2.
And you got overexcited. Yeah.
Well, you never know which one's gonna be more.
Hey. Oh, now what do we have going on? We have too much
Somebody
ADD.
called 911, so they're gonna get full response because people don't know how to properly call 911.
Oh, now there's a motorcycle cop on the scene. Oh no, I guess he's just saying hi.
What's this?
The other day, we were, in A&P, while we were just like sitting there doing paperwork and stuff, I heard a siren that was like every single siren, and then I heard a single honk in there.
Oh, no, the motorcycle cop did stop by, and they're like chatting.
Where'd that 6.027 come from?
6.022 times 10 to the 23rd, so that's Avogadro's number. If you have your mole,
Oh,
yeah.
because wait,
That's what I missed. I always miss one step.
how did we know to use that? I mean, obviously because
It was
we're
on the,
going from moles to particles.
yeah.
Moles to.
Oh, the ratio?
Yeah. I got the
Yeah.
ratio. So I got like a crazy number.
Yeah, so once you get the moles, you can't forget. Well, it's still a crazy number.
Oh, yeah.
And, we're going to the 4-6 bigs, right?
Yeah, ideally, although looking at it, I gave you 4 for one and 3 for the next.
That's the question.
Did I mess it up? Did I add some four?
Wait,
No.
but you're telling me we have molecules.
Yeah,
I
so
put down four. How about
So
that?
why are we going to molecules?
we're going to moles.
6 to 7.
Right, so look at the equation.
Oh, I see.
Yeah, because we have our Avogadro's conversion factor.
Oh, we're going backwards. Got it. Okay.
I was looking for my right one, that's fine, I'll use this one too. But yeah, right, so the Avogadro's is just a conversion factor, or a ratio, right? 1 mole is 6.022 times 10 to the 23rd things. And then, right, notice the units. So molecules cancels out, leaving us with moles, right? And then we have moles of ethane.
Wait,
What's that?
nothing.
then the next step is a mole ratio. And so you didn't have to do both of them, right? You could have picked one, or you can compare. So either you're going to compare product of CO2 or product of water. At least those are the easiest ways to do it. All right, so I'm going to do the oxygen molecules. You want to go for it? And you don't have to do both.
I
You pick
originally
one.
did both because I didn't know if there would be a way that there would be a limiting agent for one
Yeah.
section of it and another limiting agent for another. And
Yeah.
that's when I was like, okay, which one has less? So I didn't know if you were gonna throw a curveball at us, I was like, okay.
Nah. But yeah, I like that you solved two, so then we can at least do it.
So for that last step, the third parentheses, which one would that be on?
So now that's just mole ratio though, so like
That's just the
once,
mole?
yeah. So this is just telling you how to get to moles, but then once you're at moles, you just go back to the balanced equation to get your mole ratio.
Okay, okay, that makes perfect sense. So yeah, 'cause that's the part I missed.
Mm.
So I was thinking, I think. Yes. No, no, so.
Because of balance equation.
So if you look, so the top one is figuring out how much CO2 is 2 per fluid.
Alright, I'll be right back. We need more markers.
Divided by 7.2. Does that look right?
Yes, yes.
I'll do the math.
Well, if I would have rounded it correctly, it would be slightly different. Because I thought they were both 4/6. I rounded to 4/6. Oh, damn.
So it's
Like the bus has left and I'm like,
Alright, how's this looking?
who's running this down for our family?
This is looking good.
So I was bad. I did that one in 4/6.
That's fine. And it doesn't matter too much. I probably should have given you 4 sig figs, but that's what happens when I make up numbers on the fly.
Throw a 0 in there real quick, just for my sanity real quick, make me feel like, okay.
I'm not sure. Yay!
Woo!
I'm not sure if that answer or not, though.
So, people verify? It looks,
27,330?
is that what other people got?
I just, as I said, I rounded to 4/6.
Oh, yeah.
So yeah, you're right.
So now which ones are limiting reagent?
Yeah, that's a little bit.
So definitely our ethane here.
Because the other one was like 40,000.
So ethanes are limiting reagent. Let's see, what else can we do? That's
So the
fun.
ethane is, wait, so the ethane isn't, the ethane's the, yeah, that one's limiting reagent? Okay.
Yeah. Since comparing how much CO2 we're producing, yeah, ethanes are limiting reagent. So let's try another one. let's see, what do I like? So lead to nitrate, or I should say an aqueous solution
Oh, no.
of lead nitrate is combined with an aqueous solution of potassium iodide. Oops, I should have not potassium iodide. So let's start off with write the balanced equation and predict the products.
That's a solution, right?
Yeah.
Is that-
Combined with what? No, so,
Combined with the aqueous solution of potassium iodide.
You spell aqueous like A-Q-I-U-I-S?
Yeah, aqueous, like that. A-Q-U-E-O-U-S.
E-O-U-S? That's the solution, right? Next to it? An aqueous solution of lead?
Yeah.
Now that you said tacos and avocado, now all I can think about is
Aqueous solution.
what I know what I'm making for dinner tonight.
Tacos.
Now I kind of really want chorizo too, so I'm gonna make breakfast burritos for dinner.
Oh, man. So we're all coming over to your house now?
And I don't do them too crazy. I do like a roasted garlic potatoes and then like some eggs and the chorizo, and that's about it.
That's, sounds
we're
fancy.
not picky.
Yeah.
That is, you start getting fancy when you start throwing like the Cajun cheese on it and then like salsa, sour chili.
What does it say after the aqueous? Is that solution again of potassium?
Yeah, aqueous solution of potassium iodide.
Okay.
raccoon meme?
You're my friend now. We're gonna have tacos.
I have not seen this meme. All right, do we have a reaction written? You gonna go for it?
So, I don't know if it's right. I would for a double replacement.
That sounds like a good start.
Okay.
So other people felt that way? Yeah? You can erase all that, I think. I know, I'm like starving now. We talked about his tacos. And... Yeah. But clearly we should have planned like for a taco class. So I think I heard some yays. Yeah, so did everybody get this, arrive at this? And so taking this just a step a little further, so this would be your precipitate in your reaction, your lead iodide, and you could look at your solubility rules for that. So it tends to be your heavy metals that are insoluble though, so this is driving your reaction forward. But let's practice the stoichiometry part of it. So if I have 1 times 10, oh, let me add more sig figs on there. So 1 times 10 to the negative third grams of potassium iodide and 4.34 times 10 to the negative fourth. No, that's too small. Don't want to do that. To the negative third grams of lead nitrate, which is my limiting reagent. And let's calculate grams of lead iodide since this is our solid.
Are we just gonna do the 3 sig figs?
Yeah. See, we're not even at the super fun parts because this, I could be giving you molarities instead in milliliters of solution. So that'll come later. Yeah. And then there'll be one more step to get to Does anyone have our molecular weights, by the way? For lead nitrate especially, that's a big one.
Oh, for lead nitrate, 317.2.
307, is that what other people got for that one? Might double check that value.
Because lead is, I got lead at 207.2, and then nitrate.
Hang on.
Yeah, I did 16 times 3 plus the nitrogen was 14.01. I got 62.01, and then I times that by 2, so it was 124.02 for the 2 nitrates plus the 207.2. Got 330. Oh, I was off. Yeah, 331.
Okay, that sounds,
Oh my goodness.
I cheated, I was double checking with the internet. So you said 331 point?
331.
I got 208.
331.22.
So 2,
So I think
maybe you, I don't know what happened, skipped a nitrogen.
actually, that's exactly what happened.
And
On
then,
my first one, I times all, I did the oxygen times 6, but I only added 1 nitrogen.
Ah.
That's what I was going back to check what I did wrong. So I literally just missed the nitrogen.
that's why I wanted to check the number with everybody, it's easy.
So wait, what was the answer for the EBNO3?
It should be somewhere around 331.
How'd you get that again? So like, would you times the nitrogen by 2 and the oxygen by like 6? 'Cause
Yeah, so that's one way to do it, so, yeah, so we could add up, right, so 16 times 6 plus 14 times 2, or we were saying add up the nitrates, so you can do, right, 14 plus 3 times 16.
Would you get 14? Oh, nitrogen.
Yeah, so then that gives you 62 per nitrate times 2, and then add the lead to that. So either way, that you get about 331. Obviously, I didn't keep good sig figs in my calculator here, but. And then, does anyone have potassium iodide?
I got 246.298.
246.298, you said? I'll let people round. Is that what everybody else got? Nope. You got 246? I would double check this number too.
Oh, I see, I used it on, never mind. That was messed up.
Redo.
I used lead instead of iodine.
Ah,
Whoops.
I was saying like, this sounds a little high.
Sorry, 166.3.
Something like that. Potassium iodide, something like 166.
Yeah.
See. Any victims, I mean volunteers that want to go to the board that we haven't heard from? Yeah, you can go for it.
I'm just doing the,
Yeah, whichever one you want to pick, since you're first up to bat. First victim volunteer.
We do like 4 sig figs, right? Just to keep it.
Yeah.
although I'm only doing sig figs for the answers and not the.
Yeah.
Oh, I've been doing it throughout. Is that fine or? Okay. I've been doing it throughout.
Just remember that's a -3. Or it's fine.
It's not fine.
You got it. I'm sure. Someone else want to tag in? You still got it though. I believe in you. Adara?
I've got no clue.
No clue. We can walk you through it.
I like tried to do the equations for the other ones, but I kept getting different numbers from everyone else.
Let's put it up. We can walk you through it.
I haven't gotten to writing this equation yet. I've been like trying to figure out the weights.
Ah, you got the weights. All right, who else wants to go?
Could try it.
Yeah, go for it.
The third parentheses a little bit, the ratio, still a little bit confused on that.
That's fine. We can help you.
Yeah, so for like the reactants that we're using, as long as we use both of the same product, whichever of the two, it's fine, right? Or do we have to use a specific product
Or are you saying like,
for the
do you
ratio?
have to use the potassium or the?
Yeah, you have to use the, yeah.
I was suggesting using the lead iodide because we'll use that later, but
Okay.
it really doesn't matter that much who's the limiting reagent, which one you pick.
Okay, so as long as one of the products, okay.
Is it possible, well, ask her, I don't.
Are you saying, is it possible to have like different limiting reagents with different products?
Yeah.
No.
So like if you had one, you can have like the potassium iodide would be more limiting on the potassium nitrate, but the lead nitrate is more limited in the potassium iodide, for the lead iodide.
No, because it still would have just one limiting
That was
reagent.
one way more, okay.
Yeah. One of them will still run out first.
So, on both of them, got these 2 done, and then right when I got to here.
Are we doing the calculations of it?
But look, I even put 2Ki on the bottom.
You can always set it up at the very least. Uh-oh.
Am I separated?
Yeah, so you're going from moles and molecules, but right now we have grams.
Oh, I didn't consider that, okay.
So what should we put there instead, though? So we want to go right from grams to moles. So what conversion factor do we need? What info do we need?
Need the, molecular weight, right?
Yeah, so plug the molecular weight in, so we have it on the board, so you can just write that. And we can help you calculate it if you need. So 1 mole of Ki. Yeah, so use your units to help you too. So it's easy to get overexcited and start dividing by everything.
And then from here, that's when I can continue on to the moles or.
Yeah, so now it's mole ratio time. So let's see, we have, wait, what?
No?
So we don't need Avogadro's number. So now next we just need, right, our ratio to compare them.
Just the ratio.
Yeah, so we have
Just
moles.
bypassing all this stuff here.
Yeah, I'm tricking y'all, going every which way. So right here we're at moles of potassium iodide. Okay, good. So now we have our ratio. Wait, is it 1 and 1 to look back at your balance equation? Yeah. So 2 Ki, so this looks good. And I can, somebody punch in and solve, help me, I'm doing it too, but I can always make mistakes. So I get this.
I got 3.012 times 10 to the -6.
Awesome. Yep.
Yeah, that's exactly.
So 3.012 times 10 to the -6. So this is moles of lead iodide. And does someone will write the next one on the board for the lead nitrate? I like how you're just voluntolding. You could do it too.
If you want, oh, well.
Yeah, well, I'm saying Alicia could do it, though, if she's voluntolding you, but.
No, I was volunteering her.
Ah. All right.
I think she has it.
All right, who wants to put it up?
Go do it.
After I copied yours, I got it.
And put it on there.
Go do it. Go do it.
Go do it. The more you teach it, the better you learn it.
That is the best response I've ever gotten. As soon as I copied yours, I got it. We're good.
Okay, and here's the spot where I always get stuck, right here. Here's the stuck spot.
Wait, why are we rewriting this one?
You're doing the bottom one. You're doing the, lead nitrate.
Am I doing the wrong one?
Yeah, we have this one. It was on the board and then.
Well, I'm still following behind the bus, like, hey. Are we doing the other one?
Yeah, so we're doing the other one now.
Oh, well, I have to find another one.
That's fine. Forcing.
I'm always running behind.
Oh, thanks. I know I also had to pick something fire safe for my wardrobe, so.
What was fire safe?
It's a cotton shirt, it's fire safe.
I believe so. Well, now I can tell what a synthetic shirt is, which is just how to deal with it. Maybe, I'm not sure, but.
Yeah, synthetic shirts usually feel more like slippery.
Oh, those like the Under Armour shirts?
Yep.
Oh, okay, yeah, let me get those.
Synthetics are typically blends between,
Polyester.
polyester, there you go.
What was it, one something?
1.310 times 10 to the negative fifth. Wonder since you're falling behind, you nailed that one.
I had to look at your sheet.
So what do we get, 1.5 times 10 to the negative fifth?
But is it what, like,
I got 1.310,
Yeah, 1.31,
0 times 10 to the negative fifth.
yep.
Which is your
Why don't
limited
you do it,
reagent
see if I actually get that.
potassium iodide.
All right, so that's, that's our loser reagent. So that's our limiting reagent. And so now let's, of course, ask the fun questions. So with lead iodide being our limiting reagent, so how many molecules is this? So are produced, yeah, so how many molecules of our lead iodide are being produced? And of course, what is the mass?
this is in moles, right?
Oh, what's in moles?
The lead iodine?
Where? So we have it in moles up here, right?
Yeah.
So we could start here. So we have moles of lead iodide. And so now we need molecules and mass, so two separate.
Okay, so that's moles, so we have to. Because there's more negative exponents, we're therefore lesser.
This one, yeah, it's like
Yeah.
tinier. Who wants to put either one of these or both of these? Kylie, we haven't heard from you. What about with the first one or the second one?
So for that one, wouldn't the avogadro's number be on top and the mole be on the bottom?
Yeah, do you want to put it up for us?
Probably why you got the wrong answer.
If I erase this, or
Yeah, I guess it's okay if we erase it, or you could squeeze it in there.
oh no, they're right here now. So
Do everything backwards,
Well, typically you'd be right if it was possible.
right?
So now it's correct. You did this, this is correct.
Well,
This is, no, you have to wait. That's not with a lead iodide. With lead nitrate.
oh, I didn't.
Lead nitrate.
I'm just gonna erase this.
Okay, wait, stand by, retry. Wait, hold on.
Yeah, that's fine.
I feel like we might need to do like a study group before the final.
Yeah, all of you should exchange numbers.
He's just sweeping at this point, but it looks like there was some damage to the sidewalk from that. I'm not sure if that was there before.
Oh, yeah.
And so then that leaves us with molecules, right?
Yep, and that's what we want.
Well, that's happening. We also want the mass too.
Yeah,
So
we'll have to set up a different.
I was just corrected as 100% wrong.
So, right, Trey noticed unit cancellation. So again, this is just our conversion factor that's floating around. All right, so you have to determine which way it goes. So we have moles, we're trying to end with molecules. You could even put, right, well, I need molecules at the end. So then 6.022 goes on top. And what do we get for an answer?
I got if you like 4 sig figs, I got like 1.814.
And then times 10 to the,
18th power.
yep. And everybody got that?
Molecules.
Yes? No?
What is the
Potassium iodide.
potassium iodide? Potassium iodide?
Lead iodide.
Or lead. Thanks.
It's okay, I said the same thing to her last night, I was like, yeah, this should be, lead.
Same thing. And then,
I have no defense other than it starts with a P. Wait, PBI2, but
I mean, the potassium is the K and the lead is the P.
yeah. All right, do you want to do the last bit, or does someone else
sure.
want to team in?
So my question is, how come we didn't use a ratio based on?
So it wasn't necessary in this case, because we already had moles of lead, right? And we were just trying to go from moles of lead iodide to molecules, so we weren't looking at any ratios.
We already used the, so we already
Yeah.
used the ratio previously to figure out the linear rate.
All right.
Either way.
You got it?
Do you want to do the next step?
I'm not sure where to start with next step.
I can knock it out.
You want to knock it out? Really, the first step is the lead iodide weight.
So we get the weight of lead iodide? Okay.
I think you and Josh can tag team.
Yeah, tag you in.
Just, it's all unit tracking. And reading, figuring out what it's asking, because it's always like a puzzle, right? So you don't know what you're going to be given. So you always have to read. So we have lead iodide, 461 grams per mole, approximately. Thumbs up from audience. Is this what we got for lead iodide weight, too? Cool. Just checking. Okay, Google's internet is stupid slow, so I can't check. So 0.001389. So that looks pretty good. Any questions? We like that answer? All right, wait.
I didn't really write it out in the unit constellation thing, I said multiply or divide.
Well, I mean, you can do that. I just did that so that way, in case people, some people, that's how they have to do it. You did it completely fine.
Don't write it out like that, she's gonna be okay.
As long as you get the right answer, I'm okay.
Because I mean, 461, because 461 over 1 is just 461. I just put that there so that way people can see the cancellation of the elements.
Yeah, I think ultimately, I think it'd be best to work towards this if you could, just because it'll help you in higher levels of, like we said, you know, if you take like physics or other courses. Unit canceling is powerful.
It is, no, I agree with that. I just don't agree with me taking other courses.
But yeah, so unit canceling is good, but you can follow the steps on the chart, right? So that's why you have your cheat sheet to kind of help you. So then when you're setting this up and you're trying to do the unit thing, and let's say you get, you know, lost, confused, whatever, you look back at your cheat sheet, okay, does this line up? Does this make sense? And practice, 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 practice. All right, we'll take our 10-minute break so we can start lab a little